My name is Rohit Bhatia, and I would like to present Timeliner, a forensic technique for sequencing a user's past device-wide actions from a single post-crime Android memory image. This work was done in collaboration with authors from Purdue, Georgia Tech, Affiliated Institute of ETRI, Towson, and Louisiana State University. Okay. It should come as no surprise that a timeline of a suspect's past action is of interest to a criminal investigator. In fact, the entire discipline of crime scene reconstruction is dedicated to identifying and ordering a criminal's actions. This also extends to the digital world, where the investigators attempt to discover incriminating evidence by utilizing call or SMS databases, along with app-specific browser and chat logs, to create a timeline of a suspect's past actions. However, such timelines are largely incomplete, as they recover primarily from app-specific logs. They miss fine-grained actions, such as reading a text message or checking a bank account balance. Further, unencrypted logs are available for only a few apps, and the resultant combined timeline is limited to these select few apps. In essence, traditional techniques do not create a combined timeline of fine-grained user actions from all apps, which we call a device-wide timeline. As modern cybercrimes typically involve a variety of mobile apps with complex sequencing of user actions, it is of paramount interest to an investigator. To highlight the importance of a device-wide timeline, let us take this example involving Google Maps and Netflix. Is this ordering of screens a crime? No. However, is this one a crime? Possibly, because it might be distracted driving, as the user was using Google Maps and then shift over to Netflix to watch a video. As we can see, we need a device-wide timeline that recovers the past actions of a user and also needs to work even if an app is terminated. That is, the solution needs to work outside users' influence. We will revisit this example later as a practical application of Timeliner. A good question to ask is, why has traditional forensics failed to resequence device-wide timelines? It is not for the lack of need, but because they rely on persistent storage, which is limited to app-specific logs. But as various works, some of it by our own group at Purdue, have shown in recent years that volatile storage of computer and smartphone devices serves as a big pool of evidence. We also note that volatile storage is the prime location for finding fine-grained user actions that have no storage in the persistent memory. Finally, Timeliner complements prior memory forensic works with a device-wide timeline that works as another facet of evidence. Now that we are looking into volatile memory, can we find fine-grained application-generic abstractions for user actions? Turns out there is an exact abstraction for user actions, activities, which are described in the user manual as a single focused thing a user can do. Activities account for fine-grained actions such as reading a text message with conversation activity and checking a bank account balance with the accounts activity. Further, activities are very descriptive of the actions they represent. For example, they cover actions from a very generic ones, such as conversation and conversation list, to very app-specific ones, like in-call activity, quick deposit start, and movie details. A user action modeled as an activity is launched when the user interacts with the device, for example, by clicking a button. These activity launches are handled centrally by a separate process called ActivityManager service, which provides a central and device-wide solution free from user influence, such as terminating an app. Now it may look like we have found a solution, as we can use ActivityManager service supervision records maintained in activity stacks for different apps, but we find that these are also limited to single apps, as there is no ordering available between different activity stacks. Further, if an activity is launched with a back key, the records are removed from the activity stack, which brings us to a crucial point, that activity stacks do not contain the desired past state, but only the current state, which is what we want. To solve this problem, we introduced Timeliner, a device-wide solution to recover and order past activities. Timeliner works in two stages. First, Timeliner identifies various activities using key self-identifying data structure left over as the residues, and then orders the activities inferring from their allocated locations in memory. Note that building upon the rich field of data structure recovery, Timeliner takes as input a memory image and the data structure definitions, producing a device-wide timeline that complements other memory forensic techniques. We discussed the two stages of Timeliner in detail. When an activity is launched, ActivityManager service executes launch logic, creating several transient and permanent data structures as residues of execution. These residual data structures are highly interconnected as a cluster. To aid the recovery of these residual data structures, we look deeper into them, which reveals an interesting insight about their structure, that not all data structures are equal. The blue ones are the roots, which recovered individually, helping clustering and recovering the residual data structures using predetermined field value matches. Note that these data structures are also self-identifying and contain the full name of the activity that was launched. Once timeliners identified the activities with the residual data structures, the next stage is to order them. The key observation timeliner utilizes is that many memory allocators, including Android's memory allocator, follow the first available algorithm, which uses the first empty slot for an allocation. In Android's memory allocator, requests are allocated a slot of an appropriate size. These slots are organized in runs, which are also allocated using the first available algorithm. This implies that an earlier activity will have its allocated slots in the earlier slots, which will be followed by the next activity's residual data structures, and the last activity will occupy the latest slots. Simply put, the temporal ordering in the activities leads to a corresponding spatial layout, corresponding ordering in the spatial layout in the memory layout of their allocations. To perform the reverse, that is, inferring the temporal order of activities from the spatial layout of their allocations, we first represent an activity as a set of pairs, with each pair representing a run and its allocation slots. For example, in this case, we have 3 runs and 3 entries. Note that for an activity launched after another activity, it will have its allocations following the earlier allocations, but never before it. This motivates us to define 2 functions, all precede, counting the runs with all allocations of an activity E preceding another activity F, and any succeed, counting the runs of an activity E, counting the runs with any allocations of an activity E succeeding another activity F. A legitimate temporal ordering exists only if any succeed is 0, and the confidence in such an ordering is increased with more common runs, which is equal to all precede. We represent these pairwise orderings as a directed transition graph. In this case, we can see 3 edges we can add in the transition graph based from the allocation layout. Note that the transition graph can also have an erroneous edge, as is from dial contacts activity to movie details activity in this case. The reason this erroneous edge exists is because slots were recently freed up, and hence movie details activity had existing allocations in runs that were being reused by new activities. As dial contacts activity is launched, it occupies slots in these runs that recently became available, establishing an order that is erroneous. As the next activity, in-call activity, is launched, it creates a complex transition graph with an ambiguous ordering. However, such edges will always have a low weight, as it is improbable for existing allocations to share multiple runs with new activities. Further, they will connect to highly interconnected components. Hence, erroneous edges can be identified as the minimum cuts of weight less than 3. We found this assumption true in our extensive experimentation and evaluation of Timeliner. After pruning erroneous edges, we can proceed to finding the activity ordering. Once Timeliner has pairwise temporal orderings as a transition graph, various local orderings can be determined by topologically sorting different connected components. Note that there is a disconnect between player activity and launcher, as they do not share a common run, since the first runs utilized by earlier activity are filled up before the second activity is launched. However, remember that much like allocation slots, the runs of slots are also allocated according to a first available algorithm. So we can temporally order player activity and launcher in the spatial ordering of their runs in memory. This allows us to join various local orderings to form a single global ordering. As Timeliner relies on inferring from allocation layout, garbage collection has a significant impact on timeliner's recovery. Let us take this example where we have two past activities, conversation and conversation list, and also a player activity that is live on the activity stack. As a garbage collection event is triggered, we see all traces of dead activities being erased, making them unrecoverable. For the live activity, however, we see that garbage collection cleans up the transient data structures, leaving the longer lasting ones behind. We refer to such an activity as a garbage collected activity. Finally, as we saw among erroneous edges before, garbage collection frees up prior runs, potentially causing spatial disordering. This has a significant impact on timeliner's capability to create a global ordering, because if an activity is launched sometime after a garbage collection, we lose a spatial ordering and hence are unable to generate a combined timeline. To produce an accurate timeline, we take a conservative approach and join only those local orderings that do not end in a garbage collected activity. This does not prevent us from ordering garbage collected activities in a timeline, as they can still be part of a local ordering. Note that garbage collection hinders recovery of actions that occurred before the garbage collection, but does not affect recovery of actions that occur after it. We evaluated the period of garbage collection under two usage conditions: active usage with activities being raised every 2 to 3 minutes, and ideal usage with screen off. Our results show that garbage collection for ActivityManager service takes 40 to 50 minutes for active usage case, and which can reveal a substantial amount of evidence. We have evaluated Timeliner on 3 devices running 3 different versions of Android, covering a majority of current Android installations. We evaluated each device with 6 randomly picked sequences out of 10 test sequences. The order sequences contain a varying number of activities from 12 to 16, enough to ascertain a criminal's past actions. Note that the order sequence can give a different number of activities, even for the same test case. In this example, it's because Timeliner is recovering activities before the test sequence. Finally, note the Timeliner is highly accurate with a single unique ordering recovered for each test case, which is identical to the actual ground truth sequence. Timeliner's insight, the self-identifying residual data structures can help recover past actions, is generic and applicable beyond activities. We show this by extending Timeliner to recover and order broadcast, which can be understood as app actions in contrast to activities, which are user actions. Unlike activities, which produce a plethora of residual data structures, broadcasts produce a very small number of residual data structures. In this example, this leads to a transition graph with an ambiguous ordering between the two broadcasts. We use Timeliner to recover and order the actions of a spyware, from which we recover a bunch of spying actions, from active call and message spying to camera and microphone recording. Different activities and broadcasts are color-coded to highlight different apps in the device-wide timeline. Note that despite the previously mentioned ambiguity, the recovered timeline is still useful to determine when and what was compromised by the spyware. Timeliner's other insight, the temporal ordering, leads to a spatial ordering, is also generic and applicable to other memory allocators. We show direct applicability of Timeliner to most jemalloc, a modified implementation of jemalloc used across Mozilla products such as Firefox and Thunderbird. While Android manages slots of different bucket sizes, Moz jemalloc has regions of different sized bins. Both maintains runs of individual slots or regions, and also share first available algorithms for both individual slots and run allocations. Let's look back at the distracted driving case study we discussed earlier. So the case starts with the driver using the Google Maps navigation app. And as the driver is driving, he opens the Netflix app and starts a movie. He does it by going to the recent app screen, starting the Netflix app, searching for a movie. And then starting the video. Note that this is happening while the driver is driving, so it counts as a distracted driving case. And because of his distraction, it causes an accident, and he promptly calls roadside assistance. He does it by backing out of the Netflix app to the launcher screen, opening the dialer app, and placing a call to roadside assistance. After terminating the call, he restarts Netflix and rewatches the video. However, as soon as he realizes the police is arriving, he tries to erase the evidence of his crime by backing out of Netflix app, going back to recent screen, and terminating the Netflix app. The police, however, notice the recent app screen, and suspecting a termination, they try to investigate his past actions using Timeliner. Timeliner utilizes an Android emulator for its data structure recovery. Timeliner utilizes data structure definition and supporting libraries from the Android emulator to first recover crucial data structures for memory allocator from the memory image, following which it does an exhaustive search for all the various activities and orders them. As you can see from the recovered sequence, the driver was first using Google Maps, following which he went back to the home screen and started Netflix. And after he went into an accident, he starts a dialer app, places a call to roadside assistance, restarts Netflix again. But then he realizes the police is there, so he backs out of Netflix app and terminates the application. This serves as conclusive evidence of the distracted driving that was the cause of accident. In conclusion, we present Timeliner, a tool which resequences a user's past actions from an Android device. Timeliner infers temporal ordering of activities from the spatial ordering of their allocations in memory. Timeliner provides accurate reconstruction of a user action during various time scenarios and can be extended beyond activities and to other memory allocators. Thank you very much for listening. With this, I'd like to take questions.
Thank you for the interesting work. I'm Joe from Rice University. My question is that when you're analyzing the memory, how did you get that memory? It's like a physical dump, or like having the physical address, or just the process address? Or
there are a lot of tools for acquisition, which is a separate research problem.
Yeah.
And in our current work, we basically use a custom tool which requires rooted access to the smartphone device, and we dump it with the rooted access.
So you dumping whole physical address?
We're dumping the virtual memory.
Uh-huh. Virtual memory. Okay, so you start
by using by using the debugger system call to attach to the process and dumping its memory.
Got it. And your result to show that you tested the Android 6, but I'm wondering how about the Android 7 and the recent Android 8?
We tested Android 5 and 6, and I believe it should be perfectly applicable to 7 and 8 because I looked at the memory allocator code. It has not changed. And the residual data structure definitions are also very generic and applicable beyond Android versions.
Okay, but I see the Android 8, they changed the garbage collector like Marco and Swift to their copy collections, and they have some memory background limitation features. So do you consider those things the Android 8?
Yes, they've changed the garbage collection, but that does not change the fact that we recover most of our activities post-garbage collection. So it will not affect our recovery at all.
Okay, thank you.
Mm-hmm.
Okay, maybe I can ask one question. I'm very curious about, how to evade your system. So from the perspective of a criminal, they know the police are using your system and they want to confuse the forensic process. Can you talk a little bit more about what kind of tricks an attacker can play against your system?
From a device user's perspective, they don't have much control over Timeliner's operation. The only thing they can do is force a garbage collection by using multiple apps and hoping that it fills up the memory. From an app developer's perspective, they have more options. They can try to bypass the Android abstractions of activities. by implementing their own backstack, implementing their own activity lifecycle, like many apps such as browsers and gaming apps do. This, however, has limitations in the functionality then.